Hi everybody, today we're going to talk about Descriptive Statistics Part 1, Numerical Measures of Central Tendency. All right, we're going to get into detail on a couple of different, few different areas, but the learning objectives for today are to define central tendency and common types of analysis for or through mean, or arithmetic mean sometimes we call it, median, and mode. Okay? I'm going to walk you through ways to calculate the mean, the median, and the mode for ungrouped and grouped data. Now, if you remember from the last lecture, I talked about the importance of kind of keeping in your mind the difference between grouped data and ungrouped data. Today, we're going to walk through examples of how you calculate differently, all right, the mean, the mode, and the median for those types of data. All right, and then we're going to identify the chart version of different types of central tendency. So we talk about central tendency. I'll define it for you, but I'm going to also show it to you on a chart so you can start to get used to what it looks like. Okay, and it kind of wraps together the previous lecture on patterns and where we're going from here on how to work with different types of charts and ways to show information and do it efficiently. Okay. Central tendency describes the center or average value of the data. It's simple. It's really just looking at at different ways to define the center of the data. Right? An important way of looking at different types of measuring data or patterns is to try to understand kind of where the center is. It also describes the point around which most values of the data are clustered. Typically, when we look at different types of central tendency, we want to see how much is the data clustered around that central tendency and how much of it is not. If we have data that are not clustered around it, then we have a lot of variability often in the data, which is important to know. Okay? The common types of analysis for central tendency are the mean, the median, and the mode. All right, the mean, which I mentioned before, is also called the arithmetic mean, is calculated by dividing the sum of all items of the data by the number of items. Okay? For ungrouped data, in other words, there are no classes really or no intervals that we're using, and in the previous lecture we went through an example of ungrouped data. You write the mean as the mean equals the sum of all items in the data, or all observations possibly, right? Divided by the number of items in the data, right? So it would be adding up all of the items and dividing it by the total number. This can also be written as X bar, right? That stands for mean, is the sum, which is the sigma there, of the items, the number of observations in the data, divided by the total number of items in the data. Okay? The total number of observations would be another way to say that. Here's an example so I can walk you through that in case it's confusing. Water absorption test is performed using a sample of 12 bricks. The test resulted in the following observations. The unit of analysis here is percent absorption, right? So remember that at the very end when we arrive at a percentage that we're going to talk about, which is the mean. So using our formula, mean equals the sum of all items in the data, or all observations instead of items you could say, divided by the number of observations in the data. We know that this is the raw data across that line right there. And it turns out that there are 12 individual observations, right? That would be our n, or the bottom, the denominator of the equation. And the numerator is summing up all of the different values, or all of the different observations that we have from testing the bricks. All right? If we add all those up, we get 150.5. We know that the numerator, or the total number of observations, is 12 observations that have been taken. And that equals 12.54%. That's the percent absorption that would be the mean for that grouping of raw data. All right. I'm sorry, for those ungrouped data, I should say, not to confuse you. Now we're going to talk about grouped data, which has a different way of looking at the mean. All right. For this, it's necessary to determine the class midpoint, and it will come in to play in a little bit. But we have to understand what the class midpoint is first, and then we can put it into the calculation that helps us get to the mean. Class midpoint is the average of the lower class boundary and the upper class boundary. Now remember, in the previous example, I went through talking about with classes we have the upper and we have the lower class boundaries. Right? We need to remember that when we're working with the mean of grouped data. All right, so we take the sum of all class midpoints. So we're going to determine the midpoint between the lower class boundary and the upper class boundary, and we're going to multiply that times the frequencies. In other words, the amount of times that those classes appear, and we're going to divide it by the sum of all frequencies in the data, all right, in all across the classes. It can also be written as x bar, right, which equals mean. It stands for mean. Is the sum of the frequencies, the class midpoints times the frequencies. Okay, and we divide that by the sum of all frequencies. So x here means class midpoint, and the italicized f is the frequency, stands for frequency. So to give you an example of that quickly, we're going to use the same example from the previous lecture, lecture M4, where we had concrete strength testing. We took and tallied all the frequencies and we placed them into classes in this case. All right? Now we've determined the class midpoint, which I mentioned in the previous slide we have to do with group data and finding the mean. All right, so the midpoint between 32 and 34 would be 33. Okay, we know that this class of intervals of observations has occurred 4 times in the data. Right? We looked at the data in the previous lecture. You can go back and see the raw data set. We looked at the data and we had 4 observations that occurred between 32 and 34. We've determined our class midpoint for that class. Okay? We multiply those two together, and that's how we get f times x, right? Which is the numerator that we're looking for. We're actually looking for the sum of fx. Okay? If we add all of the frequencies, or sum up all the frequencies, we come to 50 observations, right? And this should check out if you go look at the previous raw data from the lecture in M4 of all the strength tests that we did. We had 50 observations of strength tests, or tubes that were crushed so that we could get the strength test. But here we have f times x, and we get the summation of all of those as well. So for group data, you remember our equation is the sum of all class midpoints times the frequencies, f times x, over the sum of all frequencies. All right? So this is the sum of all midpoints times frequencies in this column, and this is the sum of all frequencies for the classes and the group data. This is this equation written in equation format, right? Sigma fx over sigma f for the frequencies, which would be 2103 divided by 50. And we find that based on the group data and the classes that we have of with frequencies of observations within those classes, 42.06 would be our mean, right? Our arithmetic mean. All right, so is mean a good way of looking at central tendency? Well, it is in many cases. It is unique, and we use all the data to calculate that. But the problem with mean is often if you have very high values, they can skew the mean in one direction or the other, or very low values, we can skew it down low. And so that can be a problem sometimes. You need to watch and look at the data and see where you have the most frequencies, and is your are your values being skewed, and would the mean then be not necessarily representative of a population, but it's representative of your sample. So you need to be careful with that. Also, the mean can't be calculated for certain types of data, so you need to watch out for that as well. All right, now we're going to talk about median and calculating median. When the data are arranged, right, so before we talked about tallying data, well now we can actually just take the data, rearrange them in ascending to descending order. The median is simply the middle number in that order, right? If you go from the lowest value to the highest value, for example, or ascending to descending order in some way, it really is just looking at the middle number, right? As a result, the median value is a set of data. It divides the data, right? It's not saying that 50% are necessarily in relation to that middle number, but it's saying 50% of the data in the raw data set appear after that number, and 50% typically appear before that number. So it is the middle of the range of values. For ungrouped data, remember we dividing it between grouped and ungrouped data, when the number of observations n, which we talked about n before, right? The number of items in previous slides, or in this case, we're also calling it the number of observations. When it's odd, when n is odd, when the total number, when you take all the numbers and put them in order, when that total number of observations is odd, Well, then you can find the middle observation through this formula. You basically take the total number of observations plus 1 and you divide it by 2. So I'll give you an example. We have 25 observations. We're going to look at an example of this in a minute. And we want to find what the middle value is, right, of that group of observations, right? We add 25 to 1, we divide it by 2, and 13 would be the middle value. So if you had 25 observations, the 13th observation would be exactly in the middle, okay? When n is even, when the total number of observations is even, you have to calculate it by taking a sum of the middle 2 observations. So you'd look down, let's say we had 26 observations, we would have to take the 13th and 14th value, right? And we divide it by 2. And here's an example. All right, so here we have 20 observations. And in this case, we're saying it's home sales price data. If you added thousands to that, we're going from, say, land that might be at $35,000 up to an observation of $180,000 for a home, okay? We have 20 observations, right? If you count those, it's 20. So you're going to count those after you've ranked the data in some kind of order, ascending or descending. Right? Since the total number is even, it's 20, then we'll take the 2 middle observations and we add them together, we divide them by 2, and that tells us exactly what the median for this range of data would be. Okay? It would be 75 in this case. If we're talking about group data now, right, so we were switching between ungrouped and now we're talking about group data. For group data, you can find the middle observation, right, or the mth observation with this formula here, where the lower boundary is represented by LM. You add that to, right, the total frequency or the total number of observations divided by 2 minus the cumulative frequency before class median. And I know this is starting to get more and more complicated. Remember, we talked about cumulative frequency in the previous lecture so that you understand how to calculate cumulative frequency for a class. And we'll walk through an example in just a minute. And then we have the frequency of that class median value, right? So again, we're in group data, so we're back to classes as opposed to individual observations. We multiply that times the width of the class, right? The upper boundary minus the lower boundary. So, to walk through an example for you, this is the raw data I was referring to before when it comes to concrete strength tests. There are 50 individual values, which then we're going to classify. We did this in the previous lecture, and we'll do this again here. We're going to classify it into 7 classes. So we have the N here, the number of observations or the number of items is 50. We're going to turn these into 7 classes. Here's how we did that before, right? We had class intervals of 2, right? That was the upper boundary versus minus the lower boundary. 32 to 34, 35 to 37, on up. And we did a tally. We calculated the number of frequencies for values that fit within that interval, okay? And then we took the cumulative frequency, and this is, you might have wondered in the previous lecture why we were doing this. This is an example of how it can be used. So based on this class, we have 4, but when we get to this class, we take 4 plus 7, and that gives us 11. And that's how we calculate the cumulative frequencies. And the final cumulative frequency should equal the N, or the number of observations for that data that you are classifying. Okay? Again, this is the formula I gave you just a minute ago on calculating the median for group data. Based on these items here, we can fill in our formula. Here's our formula again, right? We know that the lower boundary of the class median is 41. Now, how do we know that? Okay, because we have a cumulative frequency here that tells us that 29 is right in the middle. Or if we look at this, we can see, based on the frequencies, that about half of the values are happening above this class, and about half of them are happening below that class. So that would be the class that sits at the median, right? We know that probably the middle value is falling somewhere in there. Okay, but we can also look at how the cumulative frequency is working, and we know that somewhere in here we're seeing half of 50, which would be 25, right? So that would be the 25th observation. It's going to fall somewhere within this class. So we know, therefore, that the lower boundary for that class is 41. That's what goes here, and that's what the lower boundary of the class median. The class that holds the median value, that's what sits there, okay? Then we get the total number of observations. Remember, in the raw data we had 50 total observations, so we want to put 50 there. Right, by the formula, we're going to divide it by 2. We subtract the cumulative frequency before the class median. All right, so this is where cumulative frequency comes in. We said in this previous one that this row is our class median. That is the class or interval that holds the median. The class before that had a cumulative frequency value of 21. Okay? So we put 21 here, and then the frequency of that class median, where we know the median is going to sit, is right here. That's the frequency, so we have a value of 8. And so that's what goes in the formula here. And then finally, the class width, we know that each class has 2 values as the width of the class. In other words, 34 minus 32 is 2. And so that's what goes here in the I. Okay? When we calculate that out, what we find is that 25 string tests are below 42 as a value, and 25 string tests are above it, right? So 42 would be the actual numerical median, but the 25th observation is right about where we want to be, and we can tease that out of group data with classes when we work with classes, okay? All right, moving forward. Is the median a good measure of central tendency, right? Is it a good way of looking at where the center of the data kind of sits? Well, it is unique, and that's important. It's not influenced like the mean from extremely large values or small values, right? It can't be skewed, we call that, as much. And it can be calculated for ordinal data. But there still are certain types of data, like nominal data, that can't be used in it. And lastly, we're going to talk about mode, okay? Mode is the number that occurs the most within a set of data. And that's something that is different than median, which is simply the middle value, and then mean, which is looking at the arithmetic mean, or kind of taking the sum of all the different frequencies or the values divided by the total number of values. In this case, we're really just looking at which observation, what number, for example, in a set of raw data appears the most often. Okay? Sometimes data might not have a clear mode, and sometimes there might be more than one. Sometimes we have more than one value that appears within the data set. Okay? We're going to talk about ungrouped and grouped data again. In ungrouped data, it's the value that occurs the most often. In grouped data, it's the midpoint of the class, right? We talked about classes and intervals. It's the class with the greatest frequency, right? I've changed the data in this slide from the previous example so that I can make one class have more frequency than another, so that I'm not using what's called bimodal data, where we have 2 classes with the same amount of frequency, just for example purposes, right? So you'll see, and I'll show you where I've changed it a little bit. But the midpoint of the class with the greatest frequency is called the modal class. All right, so ungrouped data again. We're just dealing with the raw data here. I've changed this one value from the previous raw data set that I showed you. You can go back and look at it. But again, we're dealing with concrete test tubes and strength tests on those test tubes. And we have 50 observations. So N is 50. In this case, if you look at all of them and you count which value or which observation occurs the most, what you'll find is that the number 40 as a strength test occurs 5 times, and therefore with the ungrouped data here, it is the mode. All right, that's what the number that we would call the mode. And we're starting to see through that there are patterns in observations and strengths that are most common. So that's important to know what's the most common. If we're dealing with group data, again, I've changed the data slightly, and I'm using the same example that I used in the previous slide. Well, we're finding that this class now has 11 observations within it, and this class has 9. Before, if you remember, that was 10 and 10, but I've changed it for the purposes of this example. Again, we have a calculation with this equation, all right, and we can assign for example, the lower boundary of the class mode to different parts of this equation. We're using the class width again, which we know is 2. And then we're using the delta. The delta sub 1 is the difference between the frequency of the class mode and the frequency of the class before class mode. Okay? And remember, class mode is simply the class or the interval that contains the highest number of frequencies, right? So in this case, this 38 to 40 is our class mode, right? Because we have 11 frequencies and it's the highest number of frequencies across the data set in all the different classifications. All right? Delta 2 is the difference between the frequency of class mode and the frequency of the class after class mode. So basically what we're doing is we're subtracting. So in this case, delta 1, we're taking 11 minus 7. Where do we get 11 minus 7? Class mode is 11 minus the class mode before it. I'm sorry, the class before class mode. So if you look at the frequency, the class before class mode is 7. That gives us a total of 4. 11 minus 7 is 4. That's our value for delta 1. And then delta 2, it's our class mode minus the class after class mode. And if you look here, 8 is the class, right? It's the interval or the class after class, the class mode, which is 38 to 40. That gives us a value of 3. We know that our class width is 2, right? Because we looked on here, 34 minus 32 is 2. And then our lower boundary of the class mode itself, right? And that should actually, that should be a 38 here. So this number is slightly off. It would be, this should be a 38, and this should be a 38 here as well. I was going off the previous example. But in this case, the class mode, remember, is the one with the highest number of frequencies, so that should be a 38 there, not a 41, which I took from the previous example. So if you put 38 here and 38 here, you'd have 39 would be our mode for this grouped class, okay? And I will change that in the slides, so when you download them, you have them. What are the pros and cons for central tendency with mode? Well, unlike mean and median, mode is useful for nominal and ordinal data, right? So that's important, is to know that because you have less levels of detail in the information in ordinal, for example, or nominal, so you can look at the frequencies by class as opposed to discrete numbers where you can really get into a lot of detail. So it works well for that. But the cons are you might have multiple points of mode for central tendency, and I'll talk about that in a minute, which is bimodal. It's not unique, and sometimes if no variable appears more than once, for example, if you have an even distribution across the observations of how many variables appear, you might not have a mode at all. All right, and now we're actually taking some of the different concepts I was talking about for measuring central tendency, and we're putting them into a graph format. The next lecture will walk you through all kinds of different graphs that help you understand ways to represent data and the meaning behind it. But in this case, we're really just using an XY coordinate plot. If you have a really symmetric set of data, that's what you'll see, kind of what we call the bell curve. If you had two modes, you remember the previous example before I changed the numbers for calculating mode, we have bimodal. So you'll have two areas where you have a high frequency of data, and that's what you can get, which will tell you a little bit about your subject as well. Sometimes you can be skewed to the left with your data, or sometimes you can be skewed to the right, depending on, again, how much information we talked about with the mean, that really high values could drive the majority of the values one direction, or low values could drive the majority of the values in one direction as well, so to the left side of the chart. That's all for today in talking about central tendency. Thank you.